Hi, in this second video discussing Bernoulli's equation, I'd like to just recap what we did in the first video. So again, Bernoulli's equation is an expression of conservation of mechanical energy for fluid moving along a streamline. So we have a fluid particle at station 1 and a fluid particle at station 2, and we're saying that its mechanical energy, meaning its pressure, its kinetic energy, its velocity, and what we're going to introduce is its gravitational kinetic energy or potential energy, are all related and they're all constant. So as one goes up, the others have to go down or change to maintain some sort of constant mechanical energy. And there's restrictions on Bernoulli's equation. The flow has to be inviscid, which means that the effects of viscosity can be neglected. Not that we're ignoring the viscous effects. It's only valid in situations where viscous effects do not really affect the flow field. The flow has to be steady state. So what we're saying here is that the pressure and the velocity will be functions of position along the streamline only. So as we move from one location to another location along the streamline, we allow for the fact that the pressure and velocity can vary. But as long as we keep our eye at one location on the streamline, the quantities P1 and V1 will not vary as a function of time. So time is not a variable. And then the last one is incompressible. So we're saying that this is the Bernoulli's equation, such as we're going to describe it, is only valid for situations where we consider the density of the fluid to be a constant. So what I've redrawn here is what the kind of picture that we utilized in the previous video for deriving Bernoulli's equation, which I will refer to again as we looked at all the forces acting on this element, and we realized that it really was just pressure forces acting on this face and pressure forces acting on that face. And we found that when we did it, it was minus dp ds times delta s. That was the pressure, and we had to multiply that by the total area of the sides of the volume. And then we said, well, some of the forces in Newton's second law, the expression of Newton's second law says that the sum of the forces has to equal the mass of the particle, or the mass of anything, times its acceleration. So in this case, we have not a full mass, but we have a differential mass, and the acceleration is the acceleration of the fluid along a streamline. And we wrote these assuming constant density. The total volume is going to be delta S times delta area. So there's my delta M term, and the acceleration term is convective. It's convective acceleration. So it's not a time-dependent term, and we wrote this as Vs times dVs ds. So just to make that clear, what is Vs? Well, Vs is the velocity of the fluid particle. So the same pressure that we used here, where we said that this was P plus delta P. I think I used P naught in the previous video. Sorry, that would be P minus delta P, and this was going to be P plus delta P. All right, so if we equate those two together, which is what we did, and we recognize, not going to write it out again, that there's a delta S delta A term and a delta S delta A term that can cancel, and we said that we can treat our differentials as algebraic quantities, so we could cancel out the ds. We ended up with an expression of minus 1 over rho dp equaled Vs dVs, and then we integrated both sides, and recognizing that we get an arbitrary constant if we do indefinite integrals, we ended up with the expression of P over rho plus v squared over 2 equals a constant. And in writing this way, I'm dropping the subscript s for the velocity along a streamline, because when we're dealing with Bernoulli's equation, that's supposed to be understood. All right, the only term that we need to add in is the effect of what would happen if the fluid particle moves along a streamline that moves at an angle. So here's my streamline now. Well, let's getting to this, let's just go back to something we all know from elementary physics and dynamics, that if I had a box of a particular weight, W, and it was going to be moving up or down this ramp, in this case, the coordinate S is going to be up the ramp, we would find out that the weight would have two components. One that is parallel and one that's perpendicular to the ramp. Well, what we're interested in right now is how much of this weight is directed up or down the ramp. And in this case, this is the component we're looking for. So this is going to be the term dWs. So the amount of the weight of the particle, right? The weight of the particle is going to be delta W. And I guess I can just write this as delta S, as delta W, the component that's along the streamline. So if we know this angle theta, and this angle theta is that angle theta, the angle of theta of the tilt of the streamline, we can just write that delta Ws is equal to delta W times the sine of theta. All right, well, the weight of our fluid particle, we already know what the volume of our fluid particle is, and we know what the mass of the fluid particle is. So delta Ws is just going to be delta M times G times the sine of theta, which will be rho delta S delta A times G times the sine of theta. Great, so this gives me the weight. So this gives me the particle, that's the weight of the fluid particle. Now, one thing, again, we have to put it in terms of it's a vector quantity. So if S is positive, its effect is negative. So it's negative, 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 negative. But that's when we're going to add it into the sum of the forces. Now, the last thing we need to do is, what about this sine of theta? We really don't want to be in terms of sine of theta. So if we recognize that some distance along the streamline, we can call it as being delta S, well, then the corresponding vertical distance we could call as being delta Z, where Z is the coordinate along which the gravity vector acts. So if I write this, then delta S times the sine of theta will equal delta Z. So just move up a little bit. We'll find out that the sine of theta will equal delta Z over delta S, and we can take this essentially in the limit, and we write this as dz ds. Alright, so this gives me, let's write out what the weight term is that acts along the streamline. It's going to be, in the way we've drawn it here, it's going to come in as a negative, so minus rho delta S delta A times G times dz ds. All right. So if I add this now into my sum of the forces terms, so I'll do it all again. So sum of the forces will equal minus dp ds times delta S times the area, delta A. Now there's the weight term, which is going to be minus rho delta S delta A times G dz ds. And all of this has to equate to the differential mass times its acceleration, which is going to be rho times delta s times delta a, that's the mass, times vs dvs ds. So let's just cancel the terms. We recognize that there's a differential volume in each one of these terms, and there's a ds in each one of these terms. So that's enough. Let's write out what we end up with. We have, I'm not going to divide through by rho yet, so we have minus dp minus rho g dz equals rho vs ds. So now we can integrate each one of these terms, and this is going to give me p plus a constant, I'll call it c1, I'll keep the negative sign in front of it, minus rho g z plus a constant, call it c2, and this is going to be equal to rho 1/2 v, I'm going to drop the subscript now, v squared plus a constant c3. Rewriting this, bringing all the terms to one side and collecting all my constants, I end up with one expression of the Bernoulli equation, which will be p plus rho g z plus rho over 2 v squared, all of that equals some constant. I can divide through by, sometimes you'll see it where they take rho and g and put them together, so then we would write this in terms of p plus gamma z plus rho over 2 v squared equals a constant. Other times we will divide through by just the density, so we would have p over rho plus g times z plus v squared over 2 equals a constant. And lastly, sometimes you'll hear people talk about pressure head. If I divide this one through by g, I'll get p, so it's rho g, so p over gamma plus z plus v squared over 2g equals a constant. So this one has units of length. So sometimes you'll talk about the pressure head of a pump being X number of feet, and that's what they're referring to. How much they're basically thinking in terms of the Bernoulli equation as to how much pressure head you have, and because the z term, you've written everything in terms of length. All right, so lastly, how do you use this? Well, again, if I have a point here and a point here, we'll call this 1, you would have a P1, a V1, and a Z1, and over here you would have a P2, a V2, and a Z2. And let's just use in this last form, you would say that P1 over gamma plus Z1 plus V1 squared over 2G equals P2 gamma plus Z2 plus V2 squared over 2G. So that's an expression where you're saying that the mechanical energy at one location has to equal the mechanical energy at a second location. All right, we'll pick up with using the Bernoulli equation and a number of examples in class on Friday, but this now gives you the full development of the Bernoulli equation.